I somehow misunderstood. I was there some weeks ago in Kiran University.
Yes.
I don't go, but recently he asked me to come and give a lecture. So I went after quite some time.
So my lecture is not going to break anything. Yeah, but having a continued interaction over a period of time, like even 1 month or 2 months, we can actually.
No, that I proposed to him. So I said that if you want, we can. All the problem solving issues and people can solve and do solutions. We can once in a while somebody can come and someone will discuss.
Yeah.
Maybe help them to prepare for something that create
Yeah.
expressions and resources online. And then we can have a talk about those things. Those can be add on, not to teach more theory. I said the theory path is not the issue. They know how to be something they are taught. I said the problem is they are not solving enough problems. At the time, much was there. He was an alumni, but he quit at some point. Srikanth, Srikanth. He was with same like batches Lakshmi Priya. Quit after that. And also there,
अभी देख के थोड़ी सबको पता है पता बताया गया कि कांग्रेस बड़ी है
Security.
कांग्रेस का डेफिनेशन सर्च से है कांग्रेस बड़ी और ऐड करेंगे डेरिवेटिव है ट्यूब का तो ये तो थ्योरम को क्या समझता है उसके बाद एक्सपेरिमेंट्री की इनइक्वालिटी बताया एरिया डिवाइड बाय वॉल्यूम और पावर प्रेशर का क्या है कि अगर सेम वॉल्यूम का चीज सब लोग उनका है ना ये वॉल्यूम का चीज सब लोग तो कौन surface area ठीक है agreed that कुछ surface area is not defined not enough translate करो तो define determinant volume
We can get started. Okay, welcome everyone to the second talk. So we will have Elizabeth Pona giving a second lecture where she will continue talking floating point.
Mr. Jen, we introduced the floating body and the convex. And so let's continue our discussion there. Mostly, of course, I'll be talking about the convex floating body because that serves more purposes because it gives us a convex set, and those are the sets we are interested in the present context. We stopped yesterday looking at examples, and I mentioned the example of the two-dimensional infinity ball where we computed the floating body, or I gave a curve that describes the boundary of the floating body. And now let's look at our other, convex body that we always look at when we discuss things to check where we are. And the other example, aside from the cube, was the L2 unit ball. So let's take the unit ball, which I denoted like so. I could have taken a ball with radius r, but let's stay with a ball with radius 1. So then we're going to compute, okay, let's say its position. So at the center is at the origin, so I we have exactly this object here. And then because Euclidean unit ball has all the symmetries that we want, the floating ball, the delta positive is given. This is again a Euclidean ball centered at 0. Now, and we have to compute the radius of this ball. So with radius, r, say, so what's the radius? So how do we get that? So here we have our construction, we get a floating body, we look at a hyperplane that cuts off delta. So this volume, which is given to us by a cap, so this is a cap of this ball with radius 1. And let's denote by capital delta the height of this cap. So we know the volume of this cap is equal to delta, and what we want to compute here is this height capital delta, and then we know that the radius is 1 minus this capital delta, obviously. So to compute the volume of such a cap, this is actually very easy because what do you get? So let me just sketch it. So this is so what do you do? Well, you use Fubini and you integrate. Say y goes from 1 minus this capital delta to 1, and then you will have this 1 minus n minus 1 dimensional Euclidean balls that have this radius. So if this here is our y, they will have radius, so y squared plus the radius in question, so it will be 1 minus y squared to the n minus 1 over 2 dy. And then that's what you'll have to now estimate from above and below to the degree of size that you needed in order to be able to handle this. And actually what it turns out this delta is of the order of 1 minus, so it's 1 minus, and this delta is of the order some constant Cn, delta to the 2 over n plus 1. And then come higher order terms. But this first term here is good enough for me. Higher order terms in, I write delta to the 2 over n plus 1. So the next order term would be delta to the 4 over n plus 1 with some coefficient and so on. Sorry, does it bother you? Right, and what is the Cn? So the Cn is equal to, we can compute exactly this constant Cn, and this is actually, we want this one, n plus 1 over the n minus 1 dimensional volume of the Euclidean unit ball, and all this gets raised to the power 2 of n plus 1. So this we can compute exactly up to the level of precision that we needed. And now let's take this and go ahead and use the floating body. So floating body, or the convex floating body, I'll just write floating body, use floating body to define a surface area. In the spirit of how Minkowski defines the usual surface area, as I have outlined yesterday, and that was done by Blaschke. So that was done first by Blaschke, and as usual, Blaschke only did it in dimension 2 and 3, but we'll already write it down in general dimension. And Blaschke also only did it for sufficiently smooth bodies, but same comments as I made yesterday. So, in order to see what kind of makes sense in this context, let's look at our example. So let's look at the L2 ball, and there we know from this result by Mathieu Meyer and Shlomo Reisner that actually this floating body, because this is a symmetric convex body, and yesterday I said I quoted this result by Shlomo and Mathieu. Here the two coincide, right? So it doesn't really matter which one we take because they are both the same. So now we want to look at this volume difference because we want to apply the idea of Minkowski to find a surface area. So we have to look at this volume difference and see what we get. So this is, of course, the volume of the unit ball. And then now we have computed the radius of the floating ball, right? So it's a ball with radius. It's again a Euclidean ball, but now with this radius. So I already factor the volume of the n-dimensional Euclidean unit ball. And then I'll have 1 minus, and then I'll have this, 1 minus Cn delta to the 2 over n plus 1, and then plus the higher order terms, and that gets raised to the power that gets raised to the power n, and hopefully I have written all the brackets. Right, so we'll get this. And that is what this is the volume of the n-dimensional unit ball, and then I'll simply, for this expression, I'll simply write that that this is equal to 1 minus n Cn delta to the 2 over n plus 1, and then come the other order terms that I don't care about. And then we'll see that what is left here is 1 minus this, so it's n times Cn times delta to the 2 over n plus 1 plus higher order terms, right? So we end up with this. And then we see if we want to apply Minkowski idea and look at now a limit as delta goes to 0, if we want to get something that, has halfway sense, what we need to do is not now divide by delta, but by delta to the 2 over n plus 1, right? So we'll look now at the limit as delta goes to 0, this guy here, and the floating body of the guy, delta to the 2 over n plus 1, and we'll see what we'll end up. All the other terms will go to 0. We'll end up this constant Cn, and then comes n times the volume of the Euclidean ball, which is just the usual surface area of the Euclidean ball. So this is what we get. And that is actually what Blaschke then also did. He defines, so now Blaschke defines the affine surface area of a convex body of C. Well, he actually uses C infinity, but let's then say C2 plus convex body. Well, again, he does only in dimension 2 and 3, but we write down the general case. Delta goes to 0, volume of K minus volume of K delta, delta to the 2 over n plus 1. He shows that this limit exists, and he says, this I'll say is the affine surface area of the convex body K. And now it is clear to us why surface area, because of its, correspondence or similar look like what Minkowski did, right? So we'll have this, and we'll think of so surface area. This is clear to us now, and about the affine we'll think about in a moment. Now, Blaschke also showed that this is equal to an integral over the boundary of K. And then we'll have the Gauss-Kronecker curvature. So I write the n-dimensional thing right away. So Gauss-Kronecker curvature at the boundary point X, and we'll integrate with the usual surface area measure, the house temperature on the boundary. Now, so here we'll have the Gauss-Kronecker curvature. Let me just write Gauss curvature to make things short. And, now finally I explain maybe what is Gauss curvature in C2 plus. So I'll do it on the side here, and I want to leave this, so please don't let me erase what I'm now putting. So but probably everybody knows anyhow. So what is, so we want to, so we have a convex body K with, and that is its boundary. And here we have a point X on the boundary, and we want to see what its Gauss curvature is. And what I'll do is I place the body such that this point X that we are talking about is the origin. And moreover, I also place it like so, that in the support hyperplane in this point is Rn minus 1. So I place, and that I can always do. And then, and in particular in this situation where we have enough smoothness, where we look at now in the Blaschke result, all that is perfectly okay. But displacement of the body I can always do like so. And then locally, so locally around X equals 0, the boundary of K can be described by a convex function. By a convex function X. So locally, say within this neighborhood around 0, I'll describe the boundary of K by a convex function F. And then we say that K is C little k at X equals 0 if F has partial derivatives up to order K at 0. So if F has partial derivatives, continuous partial derivatives, up to order K at 0. And we'll say that K is, so K is Ck if this holds for all X in the boundary of K. It's clear what I mean if I write if this holds, right? So now I have finally explained, the C2 and Ck I've been talking all the time. And now also, then what's the Gauss-Kronecker curvature? So Hn minus 1, the Gauss-Kronecker curvature at this point 0. Sometimes I also use this notation, but I think I'll try to stick with the notation Hn minus 1 because that's what we'll use later. Sometimes I use kappa sub k to indicate that it's the body we are talking about. But I hope I am not confused. Try to stick to this notation. So this is simply, so the Gauss-Kronecker curvature at this point 0 is nothing else but the determinant of the Hessian of F. And I guess we should take absolute value because we want Gauss-Kronecker curvature to be positive at that point 0. So F. So this is the Gauss-Kronecker curvature. Yep.
So is there any combinatorial constant which is missing in this expression? Because here
absolutely right, because we said here, right, that it should be this constant.
Thank you.
Very good, thank you. So right. So so this is the Gauss-Kronecker curvature, and K is C2 plus, if K is C2, and such that Hn minus 1 of X is strictly positive for all X in the boundary of K. Right? So now I have explained this notation. Good. Let me see.
So is this formula the same as the one that you get by projecting on the Grassmannian and raising it to the power, like Crofton type formula for affine surface area is the same?
Crofton type formula for affine surface area. There are Crofton type formulas for the Kremers integrals.
Yes. So I will look at the one which corresponds to the. So for the affine square mass integrals, like I project it and I raise it to the power.
Yeah, that's probably the same thing then, yeah. But yeah, we'll get to something that you were asking in a moment. Yeah, you are right, but we'll get to this in a moment.
The surface area that you get from there, isn't it the mixed, the intrinsic volume?
Yes, but you raise it to the some power, like usually you just project it and catch the volume and integrate.
Raise it to the power and you get something.
Yes, usually when affine.
Good. Yeah, we are good. Right. So now, if we look at that, then it is of course not nice that we only. It's not. Blaschke didn't care about bodies not being C2 plus. So we really didn't care about that. But we do want. We do want to. We do not want this restriction. So we do want affine surface area not just defined for bodies that are for all convex bodies. K in R. And not just for bodies that are fluid. And why? Well, we want that because these affine surface areas do appear naturally in many other parts of mathematics. So for instance, they come in, affine surface areas come in naturally in questions of approximation of convex bodies by polytopes. And maybe Matthias in his second talk will talk about this. So comes in approximation, but also in other contexts. Of convex bodies by polytopes. Good. So I will leave this. And then, but then there is a problem. Oh, I made a mistake here also. I should have said that this is of course not what Blaschke did. Blaschke did this, right? So
right, because for now plus where the two are equal, right? Whenever you put a C2 plus.
When there is a C2 plus, they are equal. They are equal if delta is small enough, but we don't care about delta definitely is small enough in this context because we look at the limit as delta goes to 0, right? So, but here, of course, I should have put, because Blaschke did not look at, for him, the convex floating body did not exist, only the floating body. So it should be this one here, but because of the sufficient regularity and as we look at the limit of delta goes to 0, that makes perfectly sense. But we know in general, this guy may not even make sense, right? So that is the, for all convex bodies, for a general convex body. But we want it for all convex bodies and not just for C2 plus bodies. And so then a natural thing to do is to do what I've already written over there. So K is now a general convex body in Rn, and what we will do is okay, let's replace this floating body, this Blaschke-Dupin floating body by the convex floating body. Then we know that guy always exists and we don't have any problems. And of course, we cannot expect to be dividing by anything else by delta to the power 2 over n plus 1 if we want something meaningful, because after all, you know, there is this example still holding that is appearing. Then this limit, so this is a theorem that was shown by Carsten Schütt and myself. So we show that this limit here for a general, so K, a general convex body in Rn. So this limit here exists, and now I haven't forgotten the constant, so it's equal to Cn, and then comes F unsurface area, okay? So what is that now? So maybe I should have written, let me write it. So this limit is equal to an integral over the boundary of K, and then I write again HA minus 1 to the power n plus 1. So I write again Gauss-Kronecker curvature at a boundary point, and we integrate with the usual surface area measure. But okay, now we have a general convex body in Rn. And I have written here the Gauss curvature, but that need not necessarily exist in a general situation. While we know from Rademacher's theorem that almost everywhere on the boundary of the body is first derivative exists, there are bodies so that the second derivative does not exist anywhere, right? So we'll have to think about this quantity here, and it has to be given the right meaning, and we can give it the right meaning, and then it's the generalized Gauss curvature that we put here. A generalized Gauss curvature set of Alexandrov and Busemann and Feller, and I think Carsten will explain a little bit about this generalized Gauss curvature. So that's good, and we'll have this. So with Carsten, we showed that this limit here exists and can be given this interpretation here. So we define now for a general convex body the affine surface area to be the above, either the left-hand side or the right-hand side. And we have a definition for affine surface area for a general convex body. Now there were other constructions can be used. Others can be used and have been used. So instead of the floating body, we can look at the illumination body and look at the volume difference and also divide by delta to the 2 over n plus 1. And if we take the limit as delta goes to 0, that also modulo a constant dn that we also know exactly gives us also the affine surface area. So this is something I proved at some point. And then there are other definitions by Leichtweis and Ludwig, which look a bit different for affine surface area, but all coincide. As it should be if you know, things are okay, so all coincide. And what else do I want to say? Yes, there are extensions also to of affine surface area definitions to a complex setting. And again, Phoebe and David Barrett did those things. So now let me write some of the properties of this affine surface area. Okay, so properties. Firstly, And this is the affine invariance. Property. So let T be an affine map on Rn such that the determinant is different from 0. Then the affine surface area of Tk is the same as the affine surface area of K. Right, so that's why. Oh, you are right. I was thinking of determinant 1 when I wrote determinant different from 0. That's right. So times determinant n minus 1 over n plus 1. Yeah, so in particular, if the determinant is 1, then we'll see it's an affine invariant. Right? And so now we have also explained that the term affine is justified from the Minkowski definition of surface area and its similarity. We'll see that the term surface area was justified, and now from this affine invariance property, we see that the term affine is justified to call this quantity affine surface area. And this affine invariance property is easy to see because we'll have this representation of the quantity. So this we now can use as the definition of affine surface area. And we have this representation in terms of a volume difference or a derivative of volume, right? So we'll see, so note to explain this, note we look at Tk, the affine image of K under this map T and its floating body. Then note that this is equal to, well, we look at the body K and divide by, and look at the floating body with index delta over the determinant of T, and T applied to this will have this identity. So why is this? Why does this last thing here hold? So proved by picture. So here we'll have Tk, we'll have a hyperplane that cuts off delta here. Then we have marched from K to Tk via the map T, but then of course we can march back from Tk to K via T minus 1, and we'll see, okay, we'll get here a hyperplane T to the minus 1 of H. So this will be again a hyperplane. And what will it cut off? Because hyperplane a linear map. So what will be cut off here is delta times the determinant of T minus 1. And that is, of course, delta over determinant T over determinant T. So this explains that, right? And now we have, and now we see, of course, immediately the affine invariance property using, you know, so to speak now, what we can take as definition of affine surface area. Namely, we see that the limit as delta goes to 0, Tk minus volume minus Tk delta volume over delta to the 2 over n plus 1. This is the same as limit delta goes to 0. I'll pull out the determinant T here, and we'll get K, and then we'll replace Tk delta by this quantity here. I can pull out the determinant, and we end up with K delta over determinant T volume, and then we'll divide by still delta to the 2 over n plus 1. But we want to make it so that it fits this here. So we'll divide by determinant T. But then we have made a mistake. So we'll fix the mistake, determinant T to the 2 over n plus 1. And then we'll see, okay, we'll see that we'll get exactly determinant T to the n minus 1 over n plus 1. And then the limit, if we put that guy here now equal to S, S goes to 0, K minus KS volume over S to the 2 over n plus 1, and that is of course nothing else but the affine surface, and I forgot the n minus 1 over. Right? So we'll see the affine invariance property immediately now, because we'll have it written as a derivative of volume. So that was the first property. Now let's write another property, namely the affine surface area of P is equal to 0 for every polytope, which we see also looking at our definition here. If P is a polytope now, I'll look at the, so let's draw our usual picture of our polytope, which is the L infinity unit ball, and then we'll see almost everywhere on the boundary, as almost everywhere on the boundary, we have that Hn minus 1 is equal to 0, right? So that's why we'll have at a polytope 0, but one may wonder, and of course on the left-hand side we'll also get that, but one may wonder one may wonder to look at this a little bit more precisely, and so let's do this in the case when we'll have our other, typical example that we always use. And I'll take the two-dimensional L infinity unit ball, for which we have computed, or I have given you the computation or the form of the floating body. And this is, if I do this volume difference, then it's enough to look at what's happening in the first quadrant, and I gave you the boundary, which was given by this function 1 minus delta over 2, 1 minus x, and that was 0 less or equal x less or equal than 1 minus delta over 2. So we compute this volume difference, that is, we compute this expression here, right? And so to get the whole thing, I multiply by 4 what we'll get in the first quadrant, and I don't do the computations because it's an easy integral. We can all do that. Let me just give you the result. So the result is what? 2. I have already put in the 2 on it. Delta minus delta log 1 over delta. Log delta, because I have written the minus here, and then plus, and then comes higher order terms that are not relevant. Actually, yeah, they are not relevant. It's just delta times another constant, log 2 or something. So that's what we get. And so if we see, now we are in dimension 2, if we divide by delta to the 2 over 3, right, which we should do when we are in dimension 2, then we will see, okay, if we do that and let delta go to 0, we'll actually get 0, right? But then maybe that's not a good idea to divide by delta to the 2 over 3, but we should divide maybe by something that gives us a limit that's different from 0, and that would be dividing by this order term, right? And then we can expect for polytopes to get something non-different from 0. And that was done in the general case, and it's a very pretty result by Carsten. I'll write it maybe here. I have another space here, but don't let me erase this. So this theory by Carsten says, if we have a polytope and we look at the volume difference of T polytope, and we look at this volume difference, and then we'll divide by delta log 1 over delta to the n minus 1, I think it is, and look at the limit as delta goes to 0, then we'll end up the number of flags. So it is related to the combinatorial structure of the boundary of the body, like affine surface area is related to the structure of the boundary of the body. This happens also for polytops. So it's number of flags of P, and then we'll divide by what cast we divide by what. Theories out, you should remember.
N to the n minus 1.
No, I just look n to the n minus 1 is right, but also an n factorial. So, and our flag is of course, you know, a flag is a flag of P is an n tuple f0, f1, and so on, fn minus 1, where each fi is an I-dimensional phase of P, and it's such that F0 is contained in F1, contained and so on, contained in Fn. Right? So for the cube, for instance, probably better to draw a three-dimensional one. So you'll start with this vertex F0, then you will march along this edge F1, and then you could take, for instance, this n minus 1 dimensional phase, it's 2-dimensional phase, and you know. All right, so
Maybe what I was saying was incorrect, right? Because if I do projection, it's always going to be positive no matter what I do.
yeah, I was not quite sure what you meant. If you meant
Yeah.
more involved curvature expressions or what you meant, yeah. So
Because then it will never be 0.
yeah, right. Most of the time it will be, yeah.
What kind of additivity properties, if any, this fund surface area would preserve, like have?
What kind of
additivity type of properties? For example, union.
Let me also. This is actually what I try to head to, and I'm hurrying because I hope I get there, because I want to finish in time. Otherwise, I'll make enemies, right? Not friends, but enemies. So.
I mean, anyway, going for early lunch.
Neo scared me. Let me. Now there's just something else that I thought I forgot to say. But okay. Yes. So now, so we'll get to that. The last thing I want to mention is, so there was this last property I want to mention first for the affine surface area is. Let me erase this. Is that when we looked at the usual surface area, there was this super important inequality which relates these two functionals for convex bodies, namely volume and surface area, namely the affine isoperimetric inequality. And now we also have an inequality that relates the two quantities, affine surface area and volume, and that is the affine isoperimetric inequality. So we also have an inequality holding that relates the two quantities, affine isoperimetric inequality. It says that the affine surface area of K versus the volume of K, and now I have to write the right homogeneity. Here is n minus 1 over n plus 1 now. This is smaller equal, it goes in this direction, affine surface area of the Euclidean ball over the volume of the Euclidean ball, n minus 1 over n plus 1, with equality if and only if K ball is not only just a ball, because we'll have the affine invariance, but if and only if K is an ellipsoid. Okay, so we have this also.
Somehow stronger than the usual isoperimetric inequality, like is it somehow stronger than the usual isoperimetric inequality, like sometimes affine things are
Actually, it's more related, as you asked, it's more not so much related to this. It's more related to, or one can actually show that this inequality is equivalent to the Blaschke-Santano inequality. So this inequality is equivalent to Blaschke-Santano. Okay, so we'll have this
Is there a big reason why the inequality goes the other way compared to the what should we expect?
let me think for a second.
Is a polytope.
For polytopes you see
Zero.
For polytopes it's zero, so
Okay.
it should go in this direction.
What was the question? Can you just, I was asking why is it going in the other direction?
Yeah. Okay.
Oh, sorry. Can we do this independently via some kind of Minkowski or some?
This one proves actually the nicest proof for this inequality goes by proof goes by Steiner symmetrization. Like this one also has a nice proof using Steiner symmetrization. But if you have the Blaschke-Santalo inequality, then one can. It's easy to prove then once one accepts the Blaschke-Santalo inequality. If one doesn't, then one does Steiner symmetrization and because what you do is so here you have your convex body, and then you Steiner symmetrize about a hyperplane, and then and then it turns out that this curvature term here increases after Steiner symmetrization. And this is, of course, the final analysis behind this is that we have a determinant relation that describes the Gauss curvature. So what's behind that curvature increases is an inequality for determinants, a determinant inequality, Minkowski determinant inequality. I want to read. Let me please. Okay, so there we were having this affine surface area now for all convex bodies. But, and that's kind of the second point that I want to do, is that these affine surface areas have been generalized to the LP affine surface areas in the LP Minkowski theorem. LP I abbreviate it and just write LP Minkowski theorem. And one of the persons that was starting this was Erwin Ludwig, who for p bigger or equal than 1 first introduced this p affine surface area. So p is now any real number. So Erwin introduced it for p bigger or equal than 1. And what did he, or how did he define it? Well, it turns out that it is this quantity here. If you read one of his papers, you may not be able to find that the expression that I'm going to write down now is what you find in his paper, original paper, but that's what it boils down to. So it's the integral over the boundary of k. And then we'll have now again Gauss curvature, but now raised to the power p over n plus p. And again, we integrate with respect to our usual Hausdorff surface area measure. But then there is an additional term coming, which is an inner product of a boundary point and its outer normal. So here we'll have the boundary of K, and here we'll have a boundary point X, and by NX I'll denote the outer normal of the boundary point. And that thing here gets raised to the power n p minus 1 over n plus 1. So this is what Irving did. He did it for p bigger than 1. And then there were notions for p between 0 and 1, and that was IB, and actually Carsten and myself. And then finally, for all p different from minus n, and that was also by Carsten and myself. So why do I say p different from minus n? Well, if you look here or here, you will see if p is equal to minus n, then we would divide by 0, which is not a good idea. However, like in Janir's talk, if one looks at things properly, one can give a definition also for p equals minus n as an L infinity, so to speak, expression, if one views that as a kind of LP norm.
So the idea is that this NX is defined almost everywhere. I mean, you're not assuming any.
NX is defined almost everywhere. That's a theory by Rademacher. Says that almost everywhere on TK, on the boundary of K, NX exists. So this makes sense, right? Now let's have a look at this so-called P affine surface area. So those are the, I instead of saying LP, I'll say it a little bit shorter, P affine surface area. So let's have a look at those and see actually what they are. I'll still keep this. And we'll see that we'll recover some familiar things. Namely, the first thing that we recover, like the first thing that we're going to have a look at is what if p is equal to 1? Well, if p is equal to 1, the exponent is 0, so this is 1, and we'll get our usual affine surface area, the one that we're talking about. So, yes, 1 of k is just what we always wrote like so, right? We are good? Now, let's look at another one, p equals 0. So if p is equal to 0, then there is no Gauss curvature present, and p is equal to 0, we'll get minus n over n, so we'll get minus 1. So a 0 of k is simply the integral over the boundary of k, and then we'll have the this inner product of our boundary point with its normal, and then so if we take a picture, is it okay if I? So if we look at a picture, what do we actually get here? Let's say 0 is somewhere in the interior of K, and then we'll have a boundary point with its outer normal, Lx. Then what is it, what we look at here when we look at this expression? Well, we look at a small surface area element, dh, n minus 1, I put that on top, right? And then times this thing here. But what is that? This is nothing else but the height of the support plane at this point to 0, right? So it's this height here. So what we look at here, what this thing here is nothing else but the volume of this little cone, or n times the volume of this little cone. And what we'll do is we'll sum up all these little cones, and that gives us n times the volume of K. So the 0 affine surface area is nothing else but the volume of the body in question. Then also one could look at P equals plus minus infinity. Then we would end up at plus minus infinity of K, which gives us an integral over the boundary of K. And then we'll bring in the just the curvature raised to the power 1, and then we'll have term involving this inner product of a boundary point with its outer normal raised to the power n just and our usual measure of integration. And if one looks at this properly and actually kind of it disappeared kind of also in the talk of Yanil, what we'll have here. See, this thing here basically is the cone measure of the body K. Because it's, give us this little cone here. What this thing here is viewed properly via the Gauss map and the inverse Gauss map. This can be viewed as the cone measure. I should put little things around this of K polar. And then the similar ideas we had done here shows that this is nothing else but the volume of the polar of K. That under the, so this is okay if K is smooth enough. C2 is probably good enough. We also notice because of the presence of this term here, because of the presence of this term here, this inner product term of a boundary point and its outer normal, we'll have to, that thing here depends on where the origin sits. So this means that we kind of, when we define the P-affine surface area, we fix now, we fix 0 as an interior point of the body when we'll talk about the P-affine surface area. And usually we'll do like, say the center of gravity is of the body is supposed to be at 0. Because of this having to fix the origin, we'll also observe that we cannot now expect that the P-affine surface area is an affine invariant as the origin needs to be fixed. The P-affine surface area is only a linear invariant. So AST property is invariant under linear transformations with determinant different from 0. Namely, we'll have the P-affine surface area of TK is determinant of T, and now it is n minus P over n plus P, P-affine surface area of K. And the next thing that I want to say is that there are P affine isoperimetric inequalities. So what are they? So they are P affine isoperimetric. I'm writing only the one for P bigger or equal than 0. So this is so the 1 over there gets replaced by the P. So with equality, if and only if K is an ellipsoid. So this is basically true for P big, or was true for P bigger or equal than 1 by Ludwig, and then there are contributions between 0 and 1 by Hu, and then all other P by my former PhD student Depigné and myself. Now, what is it that I wanted to say? Yeah. But depending on P, on the P range, so like if P, for instance, is between minus n and 0, then the inequality is reversed, right? So possibly reversing the inequality. And obviously, if I say reversing the inequality, if P is between minus n and 0, then for 0, we'll see it goes in both directions. And that's, of course, because if P is equal to 0, equality holds trivially, because we have just volume, as we just explained. Okay. Now, I want to mention one last property, which I haven't said, which the P equals 1 to is also holds. And that will be that we will be probably getting when we come to our next thing. And this is that the PFN surface area is a valuation for all P. So what's the number? ASP for all P is a valuation. So evaluation is something like a measure, or the property of evaluation is a property that holds for measures. So what is the property? It says that, and that's also maybe, what you were asking. If you have, so KL convex bodies in Rn such that K union L is again convex, then the PFN surface area of K plus the PFN surface area of L is the same as the PFN surface area of K union L plus the PFN surface area of K intersection L. So that is the valuation property. Okay. And maybe I'm just saying this, there are extensions of this idea of P affine surface area to a functional thing as well. But I'm not going to mention this, or I'm not going to write this down, I'm just going to mention it.
Now, are these things straightforward, or is this like valuation properties?
The valuation property, how you do it, so you will, let me write so K and L, right? And I have to do it in such a way that the union is again convex, so probably the L goes like so, right? What you'll do is you'll subdivide the boundary in parts where you can control what happens to the normals. So you'll divide, for instance, this part here, that would be boundary of L intersecting the interior of K, and all kinds of such configurations you look at, and then you split up your integrals according to those, and then you will put things together again.
Like the integrand behaves well with these things.
Say then?
So you're saying that the integrand behaves well with these things.
So that you know what's happening to these things, at the various situations. That's how the proof goes. Yeah. Okay, so now I want to get back to the beginning of maybe I leave this, and maybe I leave this, and I can erase it. I want to go back to the beginning of our first lecture. So we saw what was important to us there in the proof of the classical isoperimetric inequality was that we could express the volume of the Minkowski sum, or actually to be more precise, what we did, we could estimate the volume of the Minkowski sum of this expression below by using Minkowski. That was our decisive step to prove the isoperimetric inequality. And actually, so this classical, so here I mentioned this LP Minkowski theory introduced by here. The LP Minkowski theory started by Ludwig. Now the classical Minkowski theory can be characterized as is a merger of two notions, of the notion of Minkowski addition and volume, or Lebesgue measure. And that wasn't actually exactly such an idea was important to us in our proof for the classical isoperimetric inequality, because we use Minkowski to get estimates on that. But it would be much nicer if we had a even more explicit expression of that volume here. And this is actually the classical Steiner formula, which says that this volume here can be written as a sum. I goes from 0 to n. N choose I, so polynomial coefficients, and then come some other coefficients that carry information about the body and t to the I. So this is extremely nice. This volume here, let me write t. This volume here is nothing else but can be expressed as a polynomial in t of degree n with certain coefficients, and these certain coefficients are called the Fermat's integrals. The coefficients are called the Fermat's integrals, and they carry information about the body. So let's understand some of the Fermat's integrals. Let's look at t equals 0. If t is equal to 0 on the left, I'll just get the volume of k. And on the right, I only get what's left with the exponent I equals 0, right? And then we'll get n choose 0, which is just 1. So we'll get that the first Fermat's integral is nothing else but the volume. Now the second Fermat's integral, W1 of k, we see that if we now do what we did when we looked at Minkowski definition of surface area, we subtracted this term here and divided by t, right? If we do the same thing now looking at this direct expansion and let t go to 0, we'll get I Minkowski, the surface area. Okay, but on the right-hand side, I guess I should also say t goes to 0. All the higher order terms disappear, and it's just n times, I guess it's n, the first Fermat's integral that remains, right? So we'll see that this is 1 over n. So we get familiar expressions, and then the last one, the last Fermat's integral, Wn of k, actually, we can also see from what we've already done geometrically, when we look at this outer parallel body, which we'll do again here for the L infinity ball, we'll see that, okay, here we'll have t, here we'll have t, so the highest power of t is the power that corresponds to the last Fermat's integral that we have here. And we'll see from this example, oh, okay, what do we actually get? Well, we'll get those parts that are above the corner, but we have added Euclidean balls up here, so the last Fermat's integral is nothing else but the volume of the Euclidean ball. Okay, so we'll have these Fermat's integrals, and the Steiner formula is really kind of at the core of what the classical Minkowski theory is doing, like this merger of these two ideas, expressing the merger of these two ideas. So, so one would like to, in the LP in the Minkowski theory also have such a Steiner formula, which now expresses the two notions that are of importance here, which is the P affine surface area and the Minkowski sum, right? So that's what we would like for the Minkowski theory. We have a Steiner formula. We want a Steiner formula in the full Minkowski theory. And a Steiner formula should say what is the P affine surface area of K plus T times the Euclidean ball. What is that? That is what such a Steiner formula should say. And this is the theorem due to Katja Tatarko and myself. And it's actually a whole project that we have, Katja and me. And there are several papers, one in 2019 where we started to look at that, and two papers in 2023, and it is ongoing. So this is what we want, and now I need a little bit more space because we need to write something, and you will understand why once I have written the stage. So we want K convex body is our N. That is C2 plus. So for the moment, we'll say it's C2 plus. And we want T be a real number such that T is bigger or equal than 0 and smaller than the minimum of the support function of K. So support function was explained by Yanir, where we will take U in as N. Then P different from minus N, we'll have, and I have all the all that is needed. Yep. We'll have that the P affine surface area of the Minkowski sum of the outer parallel body of K. So this is equal to, now comes the sum K, I think I put the index K now, goes from 0 to infinity. And then come certain coefficients, which we call V script VPK of K. So again, those carry information about the body, T to the K. So these coefficients here we call LP Steiner coefficients in analogy to the Steiner formula over there. Steiner coefficient. And maybe I say that right away. What's the difference now? Now we don't have a finite sum, or not always a finite sum. There are instances when this sum actually reduces to a finite sum, because in general, or not always, can we expect that this sum is a finite sum. This is why we need this restriction on T in order to have convergence. In case you wonder, this comes because we not necessarily always have a finite sum. So we need to make sure that we have convergence, which is ensured by this condition here. Now the question is, of course, what are these LP Steiner coefficients, right? So we can write this in more detail. K goes from 0 to infinity, and then I'm writing how we can express this LP Steiner coefficient. Oh, sorry, I'll always mix this up. Those we call the Alpensteiner Quermass intervals, right? Because those were the Quermass intervals, the first ones. Quermass intervals. And the coefficients come now intervals. Right? Because yeah, so modulo this term here, I should call those the Quermass intervals because those were called Quermass intervals. So now, what are those? I'm still not telling you exactly what they are. I'm telling you that we can write those as a sum. M goes from 0 to k, and then comes some binomial coefficients, 1 minus t over n plus t. Choose m, k minus m, sorry. So comes some binomial coefficients, and then comes some script w p m k of k. And that, if I write equality, I have to write t. And these we call, these things here we'll call the Alpensteiner coefficients. Okay, so that is our theorem. And I'll have to tell you guys too, what are those Alpensteiner coefficients. This here. And let's get to this picture again. So we'll have the Hessian of F when we have locally described the boundary of our convex body K around, say, this point 0 by this convex function. Then the eigenvalues of the eigenvalues of the Hessian of F are the principal curvatures. Kappa I. 1 less or equal I less or equal n minus 1. So eigenvalues of these are the principal curvatures, well, I should say at the point 0 of our boundary point 0 of the body. Then the j's normalized elementary symmetric functions hj of the principal curvatures are, j goes also between 1 and n minus 1. So hj, this comes the normalization factor, n minus 1 to j to the minus 1. And then you will take all j sums, also 1 strictly smaller or equal than I1, smaller or equal than ij, smaller than ij, smaller or equal than n minus 1, kappa, I don't write the 0, I1, and so on, kappa, I n minus 1, ij, sorry. Right? And in particular, by convention, h0 is equal to 1, h1 is simply 1 over n plus 1, the sum over this kappa I goes from 1 to n minus 1, and hn minus 1 is the Gauss curvature, right?
You want n minus 1 or n plus 1?
N minus 1. As I written, I have written n minus 1. And that is so this was the mean curvature. And now that we have this, I can tell you guys what the W's are, namely it becomes complicated. So what are the LP Steiner coefficients? That is those W's. So W P M K of K is the integral over the boundary of K. Comes the Gauss curvature to the P over N plus P over. And I'll single this out because it's reminiscent of our definition that we had in the PFI surface area. So I'll keep this term apart, but there is another such term involving the a boundary point and its outer normal, and it's this one, n minus k, but I'll single this out. And then comes the sum over what indices I1 up to n minus 1. So those are positive, and they are such that the I1
I'm here.
EI2 plus. I guess I should stop not to make more enemies. So we'll get this, and even make more enemies if you see the expression I of m. So I'm not even writing those coefficients. They are very complicated. They are involving various binomial coefficients and multinomial coefficients. And then comes the product. J goes from 1 to n minus 1. And then comes n minus 1 choose j and to the ij. And then comes the hj's to the ij. And we integrate with our usual, surface area measure, the familiar surface area. So these are really, as you see, these are a bit complicated expressions, right? And it was not so easy to, establish actually that form of the expression in our proof. Also, I want to say in the theorem, we say that the body should be C2 plus, but if we look at this definition now, we can actually define it for a much more general class of bodies, not just C2 plus. We'll define it for a class that we call CP, which requires some kind of mild regularity assumption, namely that for each boundary point, there should be an inside free rolling ball and an outside free rolling ball. Then that guarantees that these expressions here and the VPKs are finite, and we studied in more detail these quantities, and they are also those quantities, the WP and the VPs. They are also valuations and have certain homogeneity properties, are invariant under rotations and reflections, and our Steiner formula is of course a more as a specific case. Our Steiner formula implies the classical Steiner formula, and I guess I should stop here. I've already made enemies because I'm 5 minutes over. So thank you very much.
Yes, lots of questions, but I'll ask a few. So, so are there any floating body interpretation? I mean, any weighted floating
We
body?
have a weighted floating body interpretation for those. This is, I think, it's in our second, in the first 2023.
Okay.
Yeah.
And I mean, how did you come up? I mean, what was the motivation to write these ASP? I mean, these P affines. I mean, how did you sort of come up with the expressions? What was the motivation? Why were you looking for them?
You mean why we were looking at this?
Yeah, exactly. How did you think about P affine?
P affine surface area?
Right.
You have to ask Orvin.
Okay.
Because he first introduced that, but it has to do with you have certain area measures and curvature measures related to the boundary of a convex body, and looking at those area measures and curvature measures, because as I said, we did write it in the form that mostly fits what I told you guys with the one affine surface area, but Irwin's approach came from surface area, from surface measures and curvature measures, and combining those.
Can I?
Yeah, yeah.
You go first. Okay, so first thing is that these symmetrized, symmetric functions or nomials of the principal curvatures, they also show up in the integral representations per mass indicators.
They do, yeah.
So
But they show up in a much more civilized
way. It's just
civilized
that,
way.
that symmetric function. So, so this expression basically must have been really just technically very difficult to just write down. And so in terms of like new idea, I'm guessing like from the Steiner formula to the PA Steiner formula is just writing down a lot of things, right?
Yeah, but on the one hand, you have to write down a lot of things and arrange things in the right way to get something. However, what you do end up with, you do end up getting new functionals on convex bodies that carry, information that we didn't know before. Because, for instance, one new information that we have here with these LP Steiner coefficients and LP Steiner Kremers integrals is that they are valuations. And you may know that there is a whole theory of valuations around. People study that, especially in the last 20 years, tremendously. And these valuations, and they are classified to be, having certain continuity properties and invariance properties with respect to certain classes of maps. And those ones, they were not known. And so they give you a new way to think about what can be done to maybe characterize some properties for convex bodies. So that was
so then, because we are connecting it to again valuations and like looking into like these things through the lens of valuations. So is there any possibility of getting, for example, we know that, so you mentioned that the ASPs are valuations which are rotation and translation invariant. So they also have
so those ones are rotation invariant. And for P equals 1, they are also translation invariant. Those one are not.
Yeah, so I'm talking about ASPs. The ASPs, they do have both the properties of rotation and translation invariant, and also have the additivity properties.
Not translation. The P's are not. They are not translation invariant because the origin has to be
equal to 1.
They are rotation invariant and invariant about under reflections. Yeah.
Okay.
Only for P equals 1, they are translation.
Yeah, but P equals to, okay, so for P equals to 1, then is there any possibility of getting the coefficients in terms of the Hadwiger formula?
This is for those. That's actually what we are trying to work out now.
I see.
That this is, one of the ongoing questions that we have. Yeah. Because it's a natural question, of course, to
decide, and also they are appearing as an infinite sum. But then the number of terms which are appearing in the Hadwiger formula are finite. So the coefficients must have some lot of information that is going on about the convex body or some.
Exactly. Yeah.
Yeah, Sarvesh.
Okay. There's in the usual Steiner formula, these WIs are given by some kind of mixed volumes, right? They can also be defined.
Mixed volumes are more like, when you look at the mixed volumes are what we typically call, you look at lambda, you not just look at two bodies and one is the ball, but lambda 1 K1 plus lambda 2 K2 plus and so on, lambda n Kn, and you can express this volume here as a polynomial, and the coefficients there are typically called mixed volumes.
Right, but these square mass integrals are sort of, they are given by mixed volumes, right? In the sense that I think W1 of K, for example, is like a mixed volume of one copy of K and n minus 1.
Okay, yeah, you can do it that. Absolutely.
So
Yes,
my
yes.
question is, are these square mass integrals also definable in some kind of mixed volume?
That would be a next step to do this.
They are mixed volumes by definition. I don't know what you mean by they're being expressed. The definition of mixed volume is those coefficients, right? I mean, you're just expressing that K plus T be in this lambda way. I mean, the definition of mixed volumes are these coefficients.
Yeah, so you'll have the mixed volumes of K1, K2, and so on, Kn.
Also, mixed volumes are translation invariant. So there would be no hope to describe these things in
Except
terms of
probably for p equals 1 or
p is equal to 1.
so those T to the what, yeah, I have to.
In terms of they are mixed volumes.
Some other kind of mixed volumes.
Yeah.
So then I misunderstood the question, because I was thinking now you mean that instead of just looking at, you know, ASP of body and the ball, one could look at K1 plus K2 and so on, right? And then, that's not what you meant, or?
No, what I essentially meant was there's a notion of mixed volumes. I mean, in that case, that you can form a notion of mixed volumes in this case also, right? And like normally mixed volumes, like at least in the classical case, there's this Alexandrov-Fenchel inequality.
Right. So the mixed volumes are the coefficients of this expansion, right?
Right.
And then there are the as you say, the Alexandrov-Fenchel inequalities related to that, right?
Yeah, so I was just wondering, like, if you find an analogous notion of mixed volumes here, you could search for a similar inequality.
We could.
That would relate these quantities and so on without having to sort of worry about it.
We do have for these quantities here and for these quantities here, we already have kind of inequalities. So we do have inequalities also already, right? Then another step, but that we are working on towards, you know, maybe this goal here, which, you know, would then correspond to what one looks at when one introduced the notion of these mixed volumes, would be to look at such a thing, right, where you have more bodies. What we are also looking towards such a goal at the moment is simply, instead of looking at K plus T times the Euclidean form, look at K plus T times L, where this is another body. So that is what we are looking at first, and we'll go from there.
I see. So I think like along these lines, so you'll have to look at like mixed volume type things, which has infinitely many coordinates. Right? You will not be able to.
Yes, that might be an issue, but we hope or we think that for that one, we are sure that we are almost sure now that we can say something, and yeah.
Maybe we have time for one last question.
Do you have any sort of?
Yeah, go ahead. I'll ask later. Yeah, go ahead. Go ahead.
Do you have any sort of derivative functions or anything to compute these things? As in, this looks like a very big expression to compute by hand. Do you have any sort of?
Can you speak up? I can't hear you.
You mean like this was very messy and
Yeah, the question was whether there is a generating function approach to compute the coefficients.
we have not found such an approach, and we really had to, you know, do computation, a lot of computations, and combine things to get it down to this form, using various Minkowski integral formulas and whatnot. Yeah. And combining terms and using properties of multinomial coefficients and things like that.
Absolute last question.
I just want to know, so p equals to 0, you get the usual standard one. So
for p equals 0, we'll get the classical Steiner form.
right, but so you give examples for 1 and plus minus infinity. So do you have any kind of thing if you put plus minus infinity or 1 is the simplification or something?
Well, if we put plus minus infinity here, that's actually also very nice because it relates to the so-called dual Quermas integrals introduced by Ludwig. So that's what the coefficients becomes. So it really fits nicely. It's a generalization of many things to one, so to speak, concept.
Equals to 1.
P equals to 1, not much. But there, nice thing is if one nice thing is when these become finite, and that happens when n over n plus p. So when p is such that n over n plus p is equal to L, where L is a natural number, then the sum becomes finite. And then there is another nice analogy. Then the last coefficient is then in this expansion here. So the last coefficient W with a corresponding p that you compute from here. The last coefficient, let me just write like so, is nothing else than the P affine, is nothing else but the P affine surface area of the Euclidean ball. And the first coefficient, or the zero coefficient, is always the P affine surface area of the body. So there is this other nice analogy that we saw here. The first coefficient is the volume, and for us, the first coefficient, WP0 of K, will always be the P affine surface area of the body. And at least in the finite case, the last coefficient will be the P affine surface area of the ball.
Okay, so I think we can end. Next time.